Let's take a look at the second collaborative problem. Find the Norton equivalent of the circuit below in the frequency domain. To do that, you will first need to calculate the impedance of the inductor. That is always equal to j omega L, which here would be 100 times 0.1 or J10. Our source looks like 10 at an angle of 45. And these two components add since they're in series. So here's our Thevenin equivalent in the frequency domain. And now let's source transform that to find the Norton equivalent. We'd have, by Ohm's law, the voltage divided by the impedance. And since the plus is on the top, the arrow will come out of the top. And we can simplify this in our calculators to come up with this answer. So this looks like it's a complex number, but in fact, it's purely real. And that is the Norton equivalent. Now let's say we were asked a slightly more complex question. Instead of finding the Norton equivalent of the circuit below in the frequency domain, we were asked to find the Norton equivalent of the circuit below in the time domain. So we need to turn this back into the time domain. To do that, we would need to convert this into two different components. And the real part would be a resistor. The positive imaginary part would be an inductor. We already know what that inductor is. It's 100 millihenries. But if we didn't see that, we could convert it. Our Z sub L is the imaginary part of this, J10. Our omega is 100. The imaginary numbers cancel, and that leaves L being 1/10 Henry, which is the same thing as 100 millihenries. Of course, we could just look up here to find it too. So now that we know that, we can convert this back into its time domain equivalent. It's a 0.707 cosine 100t current source. And it looks like it has a 10 ohm resistor in series with a 100 millihenry inductor. So if we're asked to find the same thing in the time domain, this is what we would have. If the imaginary part of our impedance was negative, if it looked something like 10 minus J10, then anything with a negative impedance would have to be a capacitor. And instead of using this equation, we would use this equation, where we could bring that J up to the top. And using this, we could now find our C.